These are sample problems based on our topic theoretical cycles. Guided problem solving number 1. An O2 engine has a clearance volume of 7% and it produces 300 kilowatt of power. What is the amount of heat rejected in kilowatts? First is to calculate the amount of heat rejected, establishing the formula, and that can be by using the thermal efficiency. So the air standard efficiency rather is net work divided by heat supplied, which can also be written for the net work, that is heat supplied minus heat rejected. So from this formula, we can get the amount of heat rejected, which is the unknown, since we already have the work net, which is 300 kilowatt of power. And then we have 7% clearance volume. So we can use the air standard efficiency formula for us to get the unknown, which is the heat rejected, if we have the heat supplied. So for the given, it is given that the net work is 300 kilowatt. So we will calculate thermal efficiency, so that if we have the thermal efficiency, we can get the heat supplied, and if we have the heat supplied, we are just going to use this formula to get the heat rejected. So for the air standard efficiency, that can be written as, for auto engine, our air standard efficiency, the shortcut formula is by using the compression ratio, and that is 1 minus 1 over compression ratio to the power of A minus 1. For air, the value of K is 1.4. So we are going to use K 1.4 since our air standard cycle, we have air as our working fluid. So we are going to solve for the unknown from this equation, which is the compression ratio, which is R. Compression ratio can be solved using the formula, the swept volume plus the clearance volume divided by the clearance volume. For the clearance volume, that can be written as a percentage of the swept volume. That is percentage, which is C of the swept volume. A certain percentage of the swept volume is our clearance volume. So by substitution of this formula to this equation here, we can erase, or we can cancel out swept volume in the equation. We just substitute VC as CVS. So we have this one, such that our compression ratio can be written as 1 plus C over C. And since we know from the given that the clearance volume is 7%, so C here is the clearance volume in percent. That is 7% in decimal rather, so that's 0.07. So just substitute 0.07 in C here, and then we can get a compression ratio, which is 15.285. So this 15.285 represents the compression ratio in the thermal efficiency formula. So from thermal efficiency formula, just go back rather to the original equation that we have. So this is formula, then substituting the known value. So we already know the R as well as the K, and then the network. So from this equation, we can solve for the heat supplied. The heat supplied is 451.779 kilowatt. And finally, we can use this network is equals to heat supplied minus heat rejected formula, so that our heat rejected is heat supplied, which is 451.779 minus network, which is 300 kilowatt. So therefore, for this auto engine, the heat rejected is 161.78 kilowatt. So as you can see, amount of heat rejected is also a substantial amount of energy since this produces 300 kilowatt, and then the heat supplied is 451. So that is around 1/3 of the total amount of heat that we supplied is wasted. So maybe we can improve this auto engine by doing some increasing the compression ratio or doing some modification. And then problem solving number 2, but before that, this is how our engine parts look like. So this is the engine parts we have here. In the previous problem, there was a mention of clearance volume. There is also a mention of swept volume. So this is how it looks like. So for the swept volume is the volume of air that the piston cylinder will swept during its displacement or during the stroke. That's why it's called the swept volume. And then not the entire cylinder is being included in the stroke or covered in the stroke. That's why the remaining volume is what we call the clearance volume. So the distance from the top dead center to the bottom dead center, that is the stroke. The stroke from the bottom dead to the top dead center, it will not reach this point here to give clearance, and that is the clearance volume. So this one here is the stroke, and then the diameter of the cylinder is the bore. And then we also have here another diagram wherein we can show now a more detailed parts. We have the stroke, we have the bore. As you can see here, this part here, this is the clearance volume. Dili na siya maabtan sa ato ang cylinder head. And then we also have the top dead center here, and then we have here the bottom dead center. And then the valves, spark plug or fuel injector. So we have here sa complete the mechanism at the engine parts. Okay, guided problem solving number 2. A gas engine working on the Otto cycle has a cylinder bore of 200 mm and a stroke of length 250 mm. The clearance volume is 1,570 centimeter cube. The pressure and temperature at the beginning of compression are 1 bar and 27 degrees Celsius respectively. The maximum temperature of the cycle is 1,400 degrees Celsius. So determine the pressure and temperature at salient points, the air standard efficiency, the work done, and the mean effective pressure. Also calculate the ideal power developed by the engine if the number of working cycles per minute is 500. As you can see here, we are given with an Otto cycle, an SVSV cycle. The cylinder bore or the diameter of the cylinder is 200 mm. The stroke is 250 mm. Clearance volume is 1,570. And we're given with the inlet initial pressure and temperature of air, that's 1 bar and 27 degrees Celsius respectively. And then the maximum temperature, that is T3, that's 1,400 degrees Celsius. We are going to calculate some quantities and also the ideal power if the working cycles per minute is 500. In order for us to calculate the air standard efficiency, we are going to use the formula for Otto cycle, the short formula. That's 1 minus 1 over RK minus 1. So looking at our given, we need to get the value of compression ratio since it is not given here in our problem. So how can we compute now for the compression ratio? So for the compression ratio, that is just again equivalent to Vs plus Vc over Vc, or the swept volume or displacement volume plus the clearance volume divided by the clearance volume. So for the clearance volume, it is given here in the problem, that is 1,770 centimeter cube. We need to find a way for us to solve swept volume. For the swept volume, we can use the formula I over 4 d squared L. Basically, this is just the volume of the cylinder. The area of the base times the stroke, or pi over 4 d squared, that's the area, and then the stroke, which is L. So D here represents the bore of the cylinder. So by substituting, just make sure that the unit is in meters. So we have diameter from the given bore is 200. So that's why we have 0.20 meter. And then the stroke is 0.25 meter. By substitution, we have the swept volume is 2,500 pi cm cube. So we just convert again from meter cube to cm cube. That's why we have cm cube here. So we can use the Vs and the Vc to get the compression ratio. So by substitution, the compression ratio is 6. And then, since we already have the compression ratio, we can now get the air standard efficiency. So the air standard efficiency is 51.16%. So this is how efficient this auto cycle is. It's 51.16%. So for the next unknown, we're going to use the diagram to calculate the temperatures and pressure at the salient points. So when we see salient points, all points, so we have 0.1, 0.2, 0.3, 0.4. The unknowns are, we are going to solve the pressure and temperatures at all of these points. So this is the TS diagram for the Otto cycle. This is a TS. This is an SV diagram. We have isentropic process 1 to 2, constant volume process 2 to 3, isentropic process 3 to 4, and constant volume process 4 to 1. So SV. And it is given in the problem that the pressure and temperature at the inlet of the compressor is 1 bar and 27 degrees Celsius. And then the maximum temperature, and that is at 0.3. So this is the maximum temperature, as you can see in the TS diagram. That's 1,400 degrees Celsius. So we are going to solve for the unknown pressure and temperatures at 0.2 and 0.4, as well as the pressure at 0.3. Calculating the temperatures using the formula that we derived from the analysis, at T1 is given, that is 27. We just have to convert it to Kelvin, so that is 315 Kelvin. And then for T2, we know that that is T1 multiplied by R to the power of K minus 1. Our R is equals to 6, so just substitute. We have 614.61 Kelvin. The temperatures at 0.2 after isentropic compression is 614.61 Kelvin. At 0.3, that is known, just have to convert it again to Kelvin. And that is the maximum temperature in the cycle of an Otto cycle. And T4, we can use T3, or we can use also T1, depending on the given. So here we can use T3. So that's T3 over RK minus 1. So that is 817.10 Kelvin. So T4 is 817.10 Kelvin. That is quite larger than T2. As you can see, the maximum temperature is 0.3. Next to that is 0.4, then 0.2, and the least is at 0.1. So these are the temperatures. These are the unknown temperatures. So for the pressure, so this is calculating the pressure. At 0.1, it's given as 1 bar. That's why we have 1 bar. At 0.2, we can use the relationship P1 R to the power of K, solve for P2. So that is 12.29 bar. And then at 0.3, we can use the relationship of combined gas law, since volume is constant. Therefore, P1 V1 over T1 is equals to P2 V2 over T2. Then we can cancel out V and then rearrange for P. So our P3 is P2 multiplied by T3 over P2. That's why, by substitution, we have 12.29 times this at temperatures, and we have 33.48 bar. As you can see here, after the compression, the pressure has increased, and even after the heat addition process, there is also an increase in pressure to 33.48 bar. And then finally, at 0.4, we can use the isentropic relationship between pressure and the volume, or the compression ratio. That's why we have 2.73 bar. So these are the temperatures and pressure at the salient points. So it is important to get them for us to get the other unknowns. The next unknown is to calculate the net work done. So for Otto cycle, the net work done, that is Q in minus Q out. So our Q in is this one. That's why it's a constant volume process. That's why it's CV. So MCV T3 minus T2, and then our heat rejection is at 0.421. That's still constant volume. That's why it's CV. So MCV T4 minus T1. So from this formula, we need to calculate first for the mass flow before we can get the net work done. For the mass flow, we can use the ideal gas equation, which is P1V1 over RT1. We are going to use P1V1 since over RT1 since the pressure and temperature there is much known to us already. So from the given, our P1 is 1 bar, that is also equivalent to 100 kPa. Our V1, so the volume at point 1 is equals to Vs plus Vc. So that is the volume at swept volume plus the clearance volume. That is the volume at point 1. So before it's compressed, no? That's at point 1. So before it compress, so the breast is the volume, that is 9.42 times 10 to negative 3 meter cube, and P1 is 315 Kelvin. So R, of course, we know that's 0.287 kilojoules per kilogram Kelvin for air. So by substituting all the values, we can get the mass entering the system is 0.01094 kilogram. So since we already have the mass, and then we also know that CV for air is 0.718, and since we already know the temperature, just plug in, then we can get the net work as 4.26 kilojoules. So the result is kilojoules because we can cancel out kilogram as well as Kelvin. So the result is 4.26 kilojoules, meaning for this cycle, the net work is 4.26 kilojoules. The next unknown is our mean effective pressure, which we can solve by using work done over swept volume. Since we already have the work done and the swept volume, we just directly plug in all of these values, and the MEP, our mean effective pressure, is 5.42 bar. So these are some important quantities, especially when you design engine later on. So you can see that mean effective pressure, the work net, the thermal efficiencies, these are performance parameters for heat engines. And then the next one is the power developed by the engine. The power developed we can get that by multiplying the net work to the cycles per minute. And the cycles per minute is given as 500 cycles per minute. That's why multiplying it by net work, we can get, and then converting the minute to seconds, we can get power as 35.5 kilowatt. The power developed by this engine is 35.5 kilowatt. So that's also a substantial amount of power. That is how you solve the different quantities for an Otto cycle. Guided problem solving number 3. So this is the problem. A diesel engine has a compression ratio of 14 and heat addition at constant pressure takes place at 6% of the stroke. Find the air standard efficiency of the engine. So for the diesel engine, air standard efficiency is different. It's quite complicated and longer than the Otto cycle. Here we have to get the compression ratio as well as the cutoff ratio. Again, the cutoff ratio is the ratio of the volume before you cut off the addition of air at that time, or fuel at that point. So that's RC, or cutoff ratio. From the given, the compression ratio is given as 15. And then for air, K is 1.4. So we need to calculate the cut-off ratio, and that is just the ratio between the volume after the heat addition process, constant pressure heat addition process, and before the constant pressure heat addition process. So that's V3 over V2. Since heat addition, V3 minus V2, this point here happens at 6% of the stroke based on the problem that the heat addition at constant pressure takes place at 6% of the stroke. Then making this into a mathematical equation, then V3 minus V2 is 0.06 of the stroke or the swept. That's why we have 0.06, and the stroke, we know that that's equals to V1 minus, the swept rather is V1 minus V2. We're trying to manipulate this one to solve for the unknown. We are going to divide everything by V2. So when you divide everything by V2, the result now will become V3 over V2, and then this one will become 1 since it divided itself. And then this one will become 0.06 V1 minus V2 minus 1. We have this equation. And then we have here some familiar term. V1 minus V2 is equals to our R. So that's why we can reduce this further to RC minus 1 minus 0.06 R minus 1. And V3 minus V2 is equals to our cutoff ratio. So the relationship between the cutoff ratio and the compression ratio based on the statement that addition at constant pressure happens at 6% of stroke can be written as in this equation. Since we already know R, then we can also calculate the cutoff ratio by direct substitution. So by direct substitution, that's 1.84. So from that, we already have RC and R, then we can get now the air standard efficiency of this diesel engine. So the standard efficiency is 61.19%. Example problem number 4. This is still a diesel cycle. The compression ratio is 16. The cylinder bore is 200. The stroke is 300 mm. Compression begins at 1 bar and 27 degrees Celsius. So this is the initial pressure and temperature. The cutoff takes place at 8% of the stroke. So this is similar to the statement a while ago. Then we are to determine the pressure and temperature at all points, the cutoff ratio, the work done per cycle, the air standard efficiency, the mean effective pressure. So first is to calculate the cutoff ratio. So from our formula, we just substitute simply, instead of using 6%, we are going to use 8% here. And then since our compression ratio is 16, then we have 16 here. And then solving for RC, our cutoff ratio is 2.2. So the cutoff ratio is 2.2. So now we can calculate the temperatures. So it's given that T1 is 27 degrees Celsius. That's the initial pressure and temperature. So converting it to Kelvin, we have 300.15 Kelvin. At point 2, using the formula, the isentropic relationship, then we have 909.9 Kelvin. For T3, we can use cutoff ratio multiplied by T1 and then RK minus 1. That's why our T3 is 2001.75 Kelvin. And for T4, that's T1 RCK. That's why we have 905.16 Kelvin. So these are the temperatures at the salient points. Solving for pressure at the salient points using formula that we already established, we can get P1 to P4 using the cutoff ratio as well as the compression ratio. So by observation, we can see that the pressure and temperature at point 3 should be the highest pressure and temperature. And then P2 and P3 are equal because heat addition happens. P2 to P3, this is a constant pressure heat addition process. So that's why we have 48.5 bar. So these are the the first unknown. So this is the PV diagram for that process. We can see here, this is a TS diagram. We have process 1 to 2, that's isentropic compression. Process 2 to 3, this is a constant pressure. This line here, the constant pressure heat addition process, that's QN. Then we have expansion, that is isentropic, and then rejection at a constant volume process between process 4 to 1. So this is how the cycle works for this cell. For the net work done, therefore, that is Qin minus Q out, we will use Qin. Our specific heat now is Cp, since this is a constant pressure process. And for the rejection Q out, that is Cv, because this is a constant volume process. So by looking at this equation, we need to calculate for the mass flow using this formula, P1 V1 over RT1. So from the given, we already know P1. And then V1 is just Vs plus Vc. So first, we are going to calculate the swept volume. The swept volume, again, using the same formula. Since we are given with the bore and the stroke, we are just going to substitute it from the given. So our swept volume is 9.424 times 10 to negative 3 meter cube. And then for the clearance volume, the equation that you can use is this one. So that's swept volume over R minus 1. So you can use the shortcut. So our clearance volume is 6.283 times 10 to negative 4 meter cube. So we can get the volume at point 1 as the sum of the two. So the volume at point 1 of air is 0.01005 meter cube. So I suggest that you use 4 to 5 decimal places, especially if the number is so small, so that it will not largely affect the results later on. Since we already have those, then we can calculate for the mass by substituting P1, V1, and RT1. The mass flow is 0.01166 kilogram. And finally, we can solve for the network using the formula by using the temperatures that we already solved. So the network is 7.74 kilojoules. Next is the air standard efficiency. So the air standard efficiency can be calculated using this formula by substituting from the given and from those that we solved. Thermal efficiency, air standard efficiency is 60.4%. And the mean effective pressure can be calculated using work over swept volume, which we also solved a while ago. By substitution, the result is in kPa, so we have to convert it to bar. So the mean effective pressure is 8.21 bar. So that's how you are going to solve the unknown quantities for a D-cell cycle. Guided problem solving number 5. An air standard dual cycle has a compression ratio of 15, and compression begins at 1 bar at 27 degrees Celsius. The maximum pressure is limited to 60 bar. Heat transferred at constant volume is twice the heat transfer at constant pressure. Calculate the pressure and temperature at the cardinal points of the cycle, the cycle efficiency, and the mean effective pressure. Okay, so for the compression ratio, that is our R, and this is the compressor inlet condition, 1 bar and 27 degrees Celsius. This is at point 1. The maximum pressure is 60 bar. So based on the diagram, the maximum pressure here are 4 and 3, they are equal. So 3 and 4, they are equal to 60 bar, based on the given here. And then the heat transfer at constant volume. So this is the heat at process 2 to 3. This is the heat addition at constant volume. It's twice the heat added at constant pressure, which is heat added at 4 to 3. So as you can see here, in a dual cycle, we have 2 heat addition process. One is at constant volume and the other is at constant pressure. And the other one is twice the constant volume is twice that of the constant pressure. So first, we are going to solve for the pressure and temperature at the cardinal points or all the points 1, 2, 3, 4, and 5. You can also expect that point 4 should be the highest temperature because it happened after two addition processes. So first, we are going to calculate the temperatures that we can solve. So far, T1 is given, that is 27 degrees Celsius. And that is at point 1, or the compressor inlet. That's 315 Kelvin. T2, we just use the isentropic compression relationship. Since this is isentropic compression, process 1 to 2. That's why we have 886.7 T. Point 3, using this formula, you can see here we have T1, we have R, but we don't have pressure ratio yet. And pressure ratio here refers to the pressure at point 3 divided by pressure at point 2. We have pressure at point 3, that's 60 bar, but we don't know the pressure at point 2, meaning we need to solve for the pressure at point 2 using the isentropic relationship between process 1 and 2, process 1 to 2. So for P1, that's given us 1 bar from the problem. P2, using isentropic compression relationship, that's P1R to the power of K. That's why P2 is 44.31. And since we already have P2 and P3 is 60 bar, then we can get RP. So since P3 is equals to P4. So RP now, or pressure ratio, is P3 over P2, that's 60 divided by 44.31 bar, and that is 1.354. So the pressure ratio is 1.354. So this pressure ratio, this will be the pressure that we will plug in here to get P3. That's why P3 is equals to 1200.6 Kelvin. So that is the temperature after the constant volume heat addition process. So from the statement, it is stated that the heat addition at constant volume is twice the heat added at constant pressure. So this is 2-3 in equation form. This is how you can write that. In equivalent formula, our Q3 happens at constant volume. That's why we can write that as CVT3 minus T2. And our heat addition at constant pressure can be written as, since this is constant pressure here, that's why it's twice CP4 minus T3. And as you can see, we already have CP and CV because these are constants for air. And these T3, T2 are already found. So meaning the only unknown here is T4, so we can get T4. By substitution and solving for T4, so our T4 is equals to 1312.73. And this is the highest temperature in the entire cycle here, in the dual cycle. The only one temperature left is T5. Before we can get T5, we need to compute first for the cutoff ratio. The cutoff ratio is the ratio 4 over ratio 3. Or that's just equal to temperature 4 over temperature T. Since this process here is constant pressure process, then we can rewrite the cutoff ratio in terms of temperature. So that's why we have cutoff ratio as 1.093. Now, since we already have the cutoff ratio, we can calculate T5 using this formula. So since we already have pressure ratio and cutoff ratio, then just simply plug in and we can get a temperature at 0.5. So that is 460.52 Kelvin. That is the temperature after expansion, isentropic expansion. And then for P5, you can use also the relationship. P5 is equals to P1 times T5 over P1. So that's why our P5 is equals, we use this relationship since we know that process 5 to 1 is a constant volume process. Then we can cancel out the volume in the combined gas law. Then we can get this one. So we have P5 is 1.53 bar. As you can see, we were able to get all the pressures and temperatures at all points. So since we already have those pressure and temperature, then we can calculate the thermal efficiency using the formula in terms of temperature. So just by plugging in, we can get the cycle efficiency as 65.98%. And for the mean effective pressure, we can use also the formula that we already derived by substitution. Then we can get the mean effective pressure as 2.77 bar. Just take note that thermal efficiency should be in decimal. And then here, we can use the bar equivalent of P1 instead of using the KPA, so that the final result will also be in bar. So those are the quantities and how we can solve them in a dual cycle. Last problem is a problem related to Atkinson cycle. We have a perfect gas which undergoes an Atkinson cycle. The gas is compressed adiabatically from 1 bar, 27 degrees Celsius, to 4 bar. The maximum pressure of the cycle is 16 bar, and we are to calculate the work done per kilogram of gas, the efficiency of the cycle, and then the mean effective pressure of the cycle. So for this gas, we will take Cp as 0.761 and then Cv as 0.573 kilojoules per kilogram Kelvin. Otherwise, if it is not given, we will just use the properties for air. And then since it's given, we are going to use this specific heat. So this is how the cycle looks like for Atkinson. As you can see here, we have process 1 to 2. We have isentropic compression. The pressure at point 1 is 1 bar, and it is compressed to 4 bar. And then according to the problem, the maximum pressure is 16 bar, so the pressure at point 3 is 16 bar. And then process 2 to 3 is the heat addition process at constant volume. Then we have an expansion at isentropic expansion, and then we have here the rejection 4 to 1, which happens at constant pressure. We have an SVSP process. So we are going to compute first all the requirements. First is calculate the specific heat ratio, knowing that this is not, we cannot use the properties for air because we have a gas here, we're given with the property. So we will use that to get for K. So for K, the specific heat ratio, that is Cp over Cv. So just plug in. So our K now is 1.328. Be careful, it's not 1.4 but 1.328. For the compression ratio, we can use the given pressure. Since this is still isentropic, then we can use the isentropic relationship. P2 is given as 4 bar according to the problem, and then P1 is 1 bar. And then our K, we solve that as 1.328. We can get the compression ratio. The compression ratio is 2.84. This is, I think it's important to solve first for the ratio before you go on to the problem, so that you can easily solve the temperatures. And for the pressure ratio, that is just the ratio from a pressure ratio of 3 and 2. So that's 16 over 4, so that's 4. Our RP is 4. So we have K, we have compression ratio, pressure ratio, and for the expansion ratio, the ratio now during the expansion process 3 to 4, the relationship is given this way, where E is the expansion ratio. So just rearranging that, solve for RE, since we have compression ratio and pressure ratio, then we can get the expansion ratio as 8.066. As you can see now, we have the expansion ratio is greater than the pressure ratio as well as the compression ratio here. So now we can solve the temperature since we already have all the ratios. So for T1, that's given 300.15 Kelvin. For T2, we are going to use the isentropic compression relationship, so that's 422.69. But take note, now our K is not 1.4 but 1.328. T3, so we have 1,690.78. You can also solve for T4 in terms of expansion ratio and compression ratio, so that's 852.47 Kelvin. Because of that, we can calculate the net work done, that is just Cv T3 minus T2 minus Cp T4 minus T1. So this work done is per per kilogram per mass. No, so that's why we don't are not going to solve for mass. So for CV, that's 0.573 from the given. Then we have P3 from the calculation. CP is 0.761 from the given. Then our net work done per kilogram is 306.3 kilojoules. For the air standard efficiency, we can use the shortcut formula in terms of the expansion compression ratio. And we have 42.15%. And finally, for the mean effective pressure, we can also use the shortcut formula in terms of efficiency. And we will have mean effective pressure of 8.38 bar. So those are the quantities that are required for this problem, and this is the way that which we can solve different quantities in an Atkinson cycle. If you have questions, feel free to chat, message, or there are questions or clarification or correction in this presentation, just message me. Thank you so much for listening.